Okay. Welcome to Math 408, Lecture 17, L functions and sphere pattern. So today we're going to finish off a beautiful formula. And I'm going to just remind us a little bit of what we've already done so far. So the first is the Fourier inversion formula. We've defined the Fourier transform. You can go from the Fourier transform back to the original function. And you have the integral of f hat of y, e to the 2 pi xy is your original function f of x. We then have if f sub t of x is just multiplying by e to the negative 2 pi I tx, it's almost like a shift in frequency, then its Fourier transform is basically just translating the Fourier transform. Then we applied Poisson summation to that function. We got the sum of f hat of n plus t is equal to the sum of fn e to the negative 2 pi I and t, because we're using the function f sub t. And we just unwound what everything was. We always assume our function is in the Schwartz space, so essentially anything you want to be true for the function is true, as long as you're reasonable, And we're going to assume a little bit more. We're going to assume f hat is band limited. So we're going to assume that the support of f hat is contained in a finite interval. You might as well adjust things to make that interval minus a half a hat. It's not a big deal. Once it's finite, center it at the origin and make it nice like this. Well, because the support of f hat is only between minus a half and it's 0 outside, the sum on the left-hand side becomes very easy to evaluate. It's just f hat of t is the sum and goes from minus infinity to infinity of f of n e to the negative 2 pi I n t. And again, the absolute value of t is less than a half. Okay? We want to get a formula for f of x. So does anybody remember the formula we're trying to prove? Maybe it was the eraser, actually.
Oh, it's the integer, right?
Yeah.
It's f of x equal to the sum from negative infinity to infinity f of n times sine.
So okay, so f of x is the sum and goes from minus infinity to infinity of f of n sine pi x minus n over pi x minus n.
Yes.
All right, if you look at this, what kind of function is sine pi x n minus n over pi x minus n? Well, let's see. Sine is odd.
It's over an even.
No, it's over an odd function.
Oh yeah. I want that too.
So if you replace x with, so think about what would happen if you replaced x with negative x. So if you replace, you've got the values of x and negative x, but you also have n and negative n. So I'll leave this as an exercise for you to just play a little bit with what's true as we replace x with negative x, and we do have the ability to change n with negative n. Is there a nice relationship? If, yes? I was going to say, if f is an even function here, you would expect to have an even function over here as well. And so maybe if f of n is f of negative n, that should push through and give you an even function if f is odd. So maybe we should expect something like that to be nice. Yes.
If
Oh,
you
so it's definitely
expand sine to its Taylor series,
Mhm.
I think it's pretty trivial. Even.
yeah.
So if you expand sign, you would get,
Still not defined at 0.
No,
oh no, it's fine at 0. Because even if x equals, well,
X equals n.
If x equals n, then if you write out the Taylor series, it'll all cancel and go rid of none.
right.
Yeah, but you're canceling the whole.
So what you would do is you would take the limit as x approaches an integer. And that's how you would define this value at an integer. You would take the limit. All right, so what we want to do is we want to try to prove that given this. So we're close. And we have Fourier inversion. So we know f of x is equal to the integral from minus infinity to infinity of f hat of t, I'll use t instead of y, e to the 2 pi I do I have to integrate from minus infinity to infinity?
No.
No, why not?
F hat of t.
I have f hat of t, and that forces.
dt.
So where do I have to integrate from?
Negative a half to a half.
Yeah, because it's being unlimited, in this special case, it's let's go from 1/2 to 1/2. So I have the integral from minus a half to a half. F hat of t, that's the sum, and goes from minus infinity to infinity. F of n, e to the negative 2 pi I n t, e to the 2 pi I xt dt. What should we do now?
Complete the square.
I'm sorry?
Can we complete the square
What square?
x, t, and t? Doesn't that come out?
Well, but we don't have x, we don't have anything to the second power. Everything is linear. For other things, completing the square is a natural thing to try.
Switch the integral on this one.
Yeah, basically we don't have that many things we can do in multivariable calculus. We can switch the order of integration, or we can change variables. Other than that, we have nothing. So if we switch, we would get a sum, and goes from minus infinity to infinity, f of n, and now we're doing an integration with respect to t, so we would have an integral from minus a half to a half of e to the 2 pi I x minus n t dt. And if you look at this, this is beginning to look like our goal. Is it hard to integrate the exponential? No, we'll just formally integrate it. If you don't like that, write the exponential as cosine plus I sine, integrate each one of these, and then collect and see it's the same. And so we get f of x is the integral, sorry, we're doing the integration. It is the sum, and goes from minus infinity to infinity, f of n, and then when we integrate, we would love to have an x minus n in front of the dt, so we have to divide by an x minus n, and we probably want a 2 pi I, so maybe put a 2 pi I x minus n, and then we would get e to the 2 pi I x minus n t, evaluated at minus a half and a half. Okay, we're almost there. So we have our sum as before. And now we can write this. This is cosine plus I sine. Cosine is evens. When we evaluate it at 1/2 and minus a half, they just cancel. So we have the I sine, and then we have the I sine again, but with t being replaced by negative a half. Since it's an odd function, the negative side comes out, takes the minus sign and reinforces, so we can get the sine of 2 pi I x minus n to the 1/2 twice. Yes? So if I've done the calculation correctly, it should be 2 sine, if we have 2i, pi x minus n, because when the t is 1/2, the t cancels with the 2 over there in the sign. And then down below, we have a 2 pi, or like the I in front of it, x minus n. And now the 2 i's just cancel. And that finishes the proof. And so we now have our interpolation formula. I think this is often called the Shannon Nyquist Whittaker interpolation. Okay. So to me, this is just an absolutely spectacular formula. If I give you certain properties about our function, I want it to be Schwartz, and I want its Fourier transform to be band limited, I just need to know the values at the integers to have it specified everywhere. That's amazing. Now, one of the things we did earlier when we were looking at interpolation formulas is we said, rather than evaluating a bunch of points, what if we evaluated fewer points but did more at those points? What if we evaluated not just the function but its derivatives? And I might have given you a homework problem involving interpolating sines and cosines. And so, I know I did this in operations research. I thought I did this here as well. If you do a simple linear interpolation between 2 points to get the intermediate, it's not bad. But if you remember that sine and cosine basically alternate for the derivatives, you can actually do a Taylor series expansion using those values at a point to approximate really well. And you can improve things. So there are situations where it is better to have fewer points and use some information about it. So there is another form of this where you use fewer points. We have to be a little bit careful as to what do we mean by using fewer points. We're using infinitely many points. It will be an infinity that is equivalent, but we'll be just evaluating at twice the n, twice the evens rather than all the alls. All right. So I emailed earlier today about how to get transcripts for the stuff for the book. I am actually working on the book right now, and my daughter has helped me, and so I'm going to go to my little book for the class and pull out the next formula. And so the more involved one is it is also equal to the sum n goes from minus infinity to infinity of f of 2n plus f prime of 2n t minus 2n times the following. Sine of pi of t minus 2n over 2 divided by pi t minus 2n over 2 squared. Okay. So this can also be proven using very similar techniques. I'm not going to assign it formally as a homework assignment, but it's not a bad thing to try to do something like that to see how can you use values of derivatives as well. You should probably be realizing that the function, sine pi x over pi x is probably an important function in a lot of this analysis. And it might be worthwhile for you to just take the Fourier transform of that, if you can, and see what it is. Or take the inverse Fourier transform and see what function came from it. So we talked a little bit last time about how you can use Fourier transforms to solve differential equations. The difficulty is at the end of the day you have to invert. So when you take the Fourier transform of derivatives, it becomes multiplying your Fourier transform by polynomials. Well, I love polynomials. I would much rather find roots of polynomials than find derivatives and stuff like that. But at the end of the day, you need an inverse Fourier transform, and you have to be able to understand where it came from. Perhaps the simplest way to do sometimes calculations like this is not to start here and do the Fourier transform, but just take a bunch of very nice common functions and start building up a table. And just look at what is the Fourier transform of some nice functions. And so I would suggest that if you've never done it before, look up some Fourier transforms of some nice functions. There's wonderful tables all through the web to just get a sense, get a feel of what's going on. Okay, any questions about this? So we're going to use this, and I wrote down notes as to exactly what we're going to use this for. So Code and Elkies were able to reduce a lot of problems on sphere packing, at least in dimensions 8 and 24, to the existence of a nice function that had certain properties. They basically needed the function and its Fourier transform evaluated the square root of 2n, and the derivative of the Fourier transform at the square root of 2n to be 0 if n was greater than a certain threshold. Yes?
What made 8 to 24 so special?
That is a long discussion. So there are certain dimensions that are nice in mathematics. And 8 and 24 are part of that.
Oh, 8 and or
8
2?
and. 8 and.
Oh.
Yes. There are other things where it's clear that as soon as you go up to a certain dimension, things become interesting. So 2 dimensions is much more interesting than 1 because you can have non-trivial paths. So if I want to go from here to here on the line, I have no choice but to go through all the points in between. If I'm in the plane, I can detour. And so if you look at applications of Green's theorem or stuff like that, the fact that we have more interesting paths in 2 dimensions is behind so much. What is the only closed curve on the line? You start and end at the same place.
Just a singleton?
Yeah, because if I go forward, I still have to come back at the end, and they cancel each other out. So basically, any closed point on the line is equivalent to a point. So I guess just as an aside, so one of the prereqs for this class is Math 150, 151, but it is not required in 150 that you do Green's theorem. Is there anybody here who has not done Green's theorem? It's okay, it's been a long time, but you've at least seen Green's theorem. Yeah. I will not let my students graduate in 150 until they've seen Green's theorem. I know this is being recorded, I don't care if they never use it, but they should at least know that it exists. It's a wonderful result. Green's theorem talks about integrating along a closed curve. What would Green's theorem look like on the real line? Yes?
The integral of a function at a point, the integral from a to a,
Yes.
of f of x dx is 0.
Or we can... Green's theorem is quite boring. The generalized Stokes theorem is the integral of d omega along some curve C is equal to the integral of omega along the boundary of C. So there's basically a nice interplay between taking the derivative of your form over the boundary and the form, the derivative of the form over the curve or the surface, whatever, and the form over the boundary. And you have to define what do you mean by the boundary operator, what do you mean by the derivative of a form. If you've seen differential forms, it's a beautiful, rich topic. We don't need it for this class, but it's just worth getting a sense of where things go. What are the obstructions? And so, why are certain dimensions better than others? Certain dimensions have interesting facts. I am not a topologist. I don't know a lot of these. Just some other ones that are worth mentioning is the cross product. What dimensions do you have the cross product? And the other dimensions?
Higher ones?
Well, it breaks down. You can kind of make a cross product maybe in 2 dimensions or 1 dimension by just saying certain components are 0 and coming up with an interpretation of what you mean. And I'm trying to remember if there was something in 7 dimensions that works for the cross product. Just other things to just quickly throw out there.
Why wouldn't it work at any higher dimensions? You have like 3 vectors in 4D.
But now you're talking about 3 vectors.
There's no guarantee that you'll have.
We're talking about an operation on 2 vectors. And so in 3-dimensional space with 2 vectors, there's a unique direction up to sign that's perpendicular to both of them.
Yeah.
And that is something special about.
I assume you could take an operation on like n minus dimension minus 1.
Right. So that would be an interesting question to investigate. Somebody can report back. Is there a generalization of the cross product where you have more things, maybe some kind of determinant? And what properties will it have? The cross product, gives you a wonderful thing. If you take 2 vectors like this, it gives you the magnitude of the cross product is the area of the parallelogram spanned by the 2 vectors. So it has geometric meaning. We have the real numbers, which is dimension 1. We have the complex numbers, r plus ir, which is dimension 2. And then people tried to find like a three-dimensional generalization, but it didn't really work. What comes next?
R plus
Quaternions?
The quaternions. And how do we denote the quaternions?
IJK.
What's the letter?
H.
It's H. And why do we use H?
Hamilton.
For Hamilton.
The college.
The college, the musical, but before that, there was the mathematician. Actually, Hamilton College is... Ooh, Hamilton College might be older than Hamilton. I'd have to check. So we have Hamilton, which is 4-dimension.
Wouldn't that imply Hamilton's older than Hamilton?
I'm sorry?
So you're saying Hamilton's older than Hamilton?
Yes. What do we have after the quaternions?
Quintians.
No.
Octonions?
The octonions. I think it's the O.
Yep.
And that's 8 dimensions.
So, is it just powers of 2 then?
But I think it stops after the octonions because as you go further, you lose more and more. When you go from the complex to the quaternions, what do you lose?
Commutativity of multiplication.
You lose commutativity. Order matters. What do you lose when you go from the Hamiltonians to the octonians?
Associativity.
Associativity. And a lot of people are just gone once associativity no longer works. I don't want to look at that. But they are useful, they do arise.
The quaternions are so good at rotating things.
Oh, absolutely.
What are octonians good at? Nothing?
I am not sure what octonians are good for. I am sure that they are good for something. Other than just, interesting exam questions. Okay, so anyways, as I was reading from my notes, from the book in progress, we will see that there is a formula where we need a function such that it and its Fourier transform and derivatives are 0 at like square root of 2n for n greater than a certain threshold, and a bunch of other properties. And if we can find such a function, then we can get good bounds on sphere packings in these dimensions. The question is, can we find such a function? And this should be reminiscent of the question I gave you earlier. If I give you a function, here's minus a half, here's a half. I want a function such that f hat is supported in here. Can you find such a function? And if you start trying to construct a function here, it's not always easy to ensure that it is band limited here. But if you start off with a band limited function, you can invert without trouble. The difficulty is putting in smoothness conditions. I want it to be infinitely differentiable. I want it to be decaying as we go to infinity. I'm not too worried about the decay, right? Because it's going to be 0 from some point onward. But I have to make sure that I have differentiability. I don't want to have discontinuities. And so one of your homework problems is to prove that such a function does exist. And so a lot of times we have these arguments. If we can find a function, then we can get the following result. It's, can we get such a function?
Some narrow, I haven't done the problem.
Right.
It seemed like some narrow Gaussian would.
No, because a Gaussian goes off to infinity.
What do you mean it really? What do you?
So I don't want to talk about what function you can do. A Gaussian would be a great thing to do, except for the fact that it goes off to infinity. You can make the Gaussian so narrow that effectively the probability of being outside, the magnitude of being outside is as small as you want, but it is not band limited.
If you subtracted.
So I don't want to go into details about what you can and cannot do. I'll give just one related example of things you can't do. So danger. This is one of my favorite problems. Find a nice sequence of functions fn such that the integral minus infinity to infinity, let's do minus 1 to 1 of fn of x dx, take the limit as n goes to infinity, does not equal the integral from minus 1 to 1 of the limit of fn of x dx. So we've been talking about interchanging limits all the time. There are times when you cannot do this. And I'm not going to worry about a couple of n's in the beginning. This is a limit as n goes to infinity. I can assume my n is at least 2,000. So here's 1. Here is 1 over n. Here's, let's do 1 over 2n. And then we will do, we'll do 1 over n. We'll do 1 over n plus 1 over 2n. And we'll do 1 over n minus 1 over 2n. So I have something of thickness 1 over n. I'm sorry, of thickness 1 over n. And I can take my function to be a triangle like this. My function will be continuous. And what is the area under the triangle? I'll make it have height 2n. 1. So each of these integrals is going to be 1. What's the limit of the fn's going to be? Which flat line?
0.
0. Because you give me any choice of x, and I eventually choose n so large that 1 over n plus 1 over 2n is less than x. So point-wise, for every x, the limit of fn is 0. You might say, well, what about x equals 0? Well, that's why I was very careful here to make sure that this is always to the right of 0. And so fn of 0 is always 0. And 1 does not equal 0. What breaks down? Why can't we interchange the limit and the integral? Other than they give different answers.
It's not uniform.
Yeah, it's not uniform convergence. The problem is this function is spiking up. It's not bounded by anything.
Was that Leibniz?
Which,
That where you can interchange golden integral?
no, this would be, I think, after Leibniz. If you're doing measure theory, you would have like your dominated convergence theorem, your monotone convergence theorem, your Fatou's lemma. This violates the conditions of the monotone convergence theorem because it's not bounded. Oh no, that's the dominated, sorry. It's violating the dominated convergence theorem. It's probably violating the monotone convergence theorem as well, because otherwise I could use the monotone convergence theorem.
Yeah.
So if you know the MCT, the DCT, and whatnot, you can find a reason why this is not permissible. It violates one of the conditions. And this just shows you why these conditions are necessary. We, for the most part, freely interchange orders in our class. We often say, well, if we take the absolute values, everything is fine, everything is nice, we can go through with it. But it's worth just reminding you of how careful we have to be. I am extremely proud that I have one paper in my published works where I do use the dominated convergence theorem. It is actually a paper on information theory and statistics, and just showing that it's, I think, something related to a Cauchy or power distribution. A certain statistical result actually provides no information, but I'm happy that my collected works, at least once in my life, I have used the dominated convergence theorem professionally. All right, so moving forward, there's a couple of items that we need. I'm not sure if this is actually recording volume. And so that would be interesting if this is causing trouble again. All right, so hopefully I was yelling loud enough that it would work. All right, I'll try again. And so we need a little bit of potentially linear programming and a little bit of modular forms. And so I thought I would start first with a little bit of modular forms and just trying to define the basics of what we need. And so this is going to be an interesting challenge because it is a very rich subject. And I don't want to go into too much detail. I want to basically just give you enough to get a sense of what's going on and why we're here. So, the path to modular forms. So we start off with the Riemann Zeta function. So zeta of s is the sum and goes from 1 to infinity of 1 over n to the s. It's the product over primes of 1 minus 1 over e to the s inverse. This is called the Euler product. almost anything you want in mathematics. The question is, when are you studying something that's worth studying? I'm sorry, yeah, I mean, if Euler or Gauss are looking at it, it's not a bad idea that there's something to it. And one of my friends from graduate school, Manjul Bhargava, one of the big reasons he has a Fields Medal now is he was looking at some problems from Gauss and came up with new ways of looking at things that people had not seen in the intervening centuries. You are often strongly encouraged to go and look at the masters. You know, what have they studied?
It's hard not to on Euler.
Well, they did a lot, and amazingly, a lot of their papers are still readable. For some of Euler's work, the analysis is not as rigorous as we would like from today's standards, but he's finding good stuff.
Heralded.
Who else would you put in that category of maybe the analysis wasn't as rigorous as possible when they started, but boy, were they observing stuff worth observing?
Fourier.
Nope. For my yes, Fourier, yes, but there's one person in particular as a number theorist.
Not Gauss.
Not Gauss. Just some incredible relations, Ramanujan. And so you have the famous story of Ramanujan sending his work, or a subset of it, to the great Hardy. Hardy was not the first person he mailed. I think he was the second. And as a professor, we love, of course, anonymous submissions from all over the world. It makes our day to get such papers. And we try to free up whatever time we can to quickly give our full attention to something like that. And so part of the miracle is that somebody took the time to look at this. And in some of the versions of the story, you basically have your Hardy at first wondering, what is this? These are just such wild, outrageous propositions. And he goes, well, but what would it mean for somebody to even just think of writing down something like this? If this is false, why would you be writing? And he starts playing with some of the stuff.
The stuff he said was like all related to sums, right?
A lot of it was sums, continued fractions, incredible identities. If you've never read a mathematician's apology, it's Hardy's trying to justify his existence of life. I talk about baseball, he talks about cricket. It's for people who think baseball is too fast-paced. You have these wonderful multi-day games. It is worth reading a mathematician's apology on his reflections on his life. So we have the Vemma and Zeta function. We've talked about how if you see the names like Euler, probably worth looking at. This has an Euler product, which represents a sum over the integers to a product over primes. For those of you who've done complex analysis, when you see a function, what do you want to do to it in complex analysis?
Analytically continued.
Analytically continued is a good start, yes. So we will assume our function's been analytically continued. Once we've done that,
Rotate.
no. You take the logarithmic derivative. It's one of the most useful things we have, and then do a contour integral. This is very similar to if you have a product, you take a log, and the log makes the product a sum. If I take the logarithmic derivative, or if I take the derivative of zeta of s, it's a pain to work with the sum. But if I take the logarithmic derivative, the log of zeta of s is the same as the sum over p on negative 1 comes out, 1 minus 1 over p to the s, with the log of product. Because the log of a product is the sum of the logs. And now if we take the derivative, we get zeta prime of s over zeta of s is negative sum over p. The derivative of that is going to be 1 minus 1 over p to the s. P to the negative s is e to the negative s log p. So when you take the derivative of this, what happens? We would get a negative log p coming out. And we have a negative in front of that, and we have a negative here. So we have 3 negatives, so it stays negative, and we get log p times p to the minus s And this is the same as negative sum over p log p over p to the negative ns. P prime n a natural number. 0, 1, 2, da, da, da. So just writing it out a little bit more expansively, sum over p, sum n goes from, oh no, we were starting at 1. And goes from 1 to infinity, log p over p to the ns. And this is just from expanding the geometric series down below, and because we have a p to the minus s in the numerator, the first term is going to be 1 over p to the s, not 1 over 1. We actually have a nice formula for the logarithmic derivative of the zeta function. And if we do contra integrals, we can exchange, hopefully, integrals with sums, and we can hopefully deduce things. This is why we love having an Euler product. If something doesn't have an Euler product, we often don't want to consider it. Maybe that's a little harsh. We'll still study the function, but we don't expect things to be the same when we look at functions that don't have an Euler product. And there are functions like that, and they do not always satisfy the generalized Riemann hypothesis. So some of them are known to have zeros that do not have real part 1/2 in the critical strip. Okay. So the question is, and this is one of the central questions of the course, how can we generalize what we're looking at? So we started with zeta of s is the sum and goes from 1 to infinity of 1 over n to the s. How might you generalize this? I want a new function that looks similar to this. What would you change? There's a couple of ways you can change things. Some are better than others. Any thoughts?
Make it alternate.
Okay. So what are you? How are you making it alternate?
Put a negative 1 to the s.
Okay.
Or negative 1 to the n, sorry.
Okay, so one is, and this would be like the eta function, which we've actually seen. It's the sum and goes from 1 to infinity of negative 1 to the n plus 1 over n to the s. I think it's often defined as n minus 1, not n plus 1. I don't know why I like the plus sign. I'm a positive person.
I do n plus 100.
Whoa.
That won't
Wait,
work.
n plus 100 won't work.
101.
101 is different. It gives me memories of 1984. Room 101. So, what did you do going from here to here? You replaced the 1 with negative 1 to the n plus 1. More generally, what could you do?
Replace with any root of unity.
You could do any roots of unity. Or more generally, just look at the sum and goes from 1 to infinity of a n over n to the s. And just throw in whatever ans you want. You can do this for any sequence an. Almost every choice of an, this will be useless. The whole point is you want to have a function where at the end of the day, it has a nice global equation. Where you take this local data, you piece it together, and you have this nice object at the end. Has everybody here seen Benet's formula for Fibonacci numbers?
Yes.
Everyone has seen Benet's formula? Okay, so in Benet's formula, have you seen the proof by generating functions? How many people have not seen proof by generating functions?
I don't think I've seen that.
Okay. I will probably do that maybe next class. But what you do is you start off by looking at the sum, and it goes from 0 to infinity of fn x to the n, and call that g of x. And it turns out g of x has a nice form. If memory serves, I think it's x over 1 minus x squared. I would probably quickly do it right now. So we'll define the Fibonacci as f0 equals 0, f1 equals 1, dot, 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 dot. And then what you do is if you look at the sum and goes from 2 to infinity of fn x to the n, this is, of course, fn plus 1, I'll do this way. Fn is fn minus 1 plus fn minus 2. If I look at this, this is going to be fn minus 1 x to the n plus the sum of fn minus 2 x to the n. And then it goes from 2 to infinity. I have fn minus 1 x to the n. So really, I'll write x to the n as x to the n minus 1 and pull out an x. And over here, I'll write xn as xn minus 2 and pull out an x squared. This function over here is g of x minus f1 x to the first, which is just x, minus f0 x to the 0th, which is just 0. That equals x. Well, if I just change my index of summation, this is just something from 1 to infinity of fn x to the n. That's just x g of x. And over here, this is x squared g of x. You can now use this to solve for g of x. And I would get 1 minus x squared times g of x is equal to x bringing it over, and there's the formula. So we took our local data, and we created this generating function, we put it all together, and we got this global object. And the absolute miracle here is that we can now use this to get information about the local objects. So to some extent, once I give you the definition of the Fibonacci numbers, all the mystery is gone. Everything is completely determined. Right? If you wanted the billionth Fibonacci number, could you find it? Yes. Would it be pleasant? Hell no. If you're just doing the additions, but you're just adding adjacent numbers, you can just march down. The value of Binet's formula is we can jump. What is the least favorite integration technique from Calculus 2? Partial fractions, right? If I'm asked which of my kids is my favorite, I don't answer that. When they were young, it was whoever slept better throughout the night. Now that they're older, I won't answer questions about which kid do I like the most. Integration techniques, we are allowed to make fun of integration techniques. Almost no one likes partial fractions when you're ordering what would I love to have to apply. But partial fractions is extremely valuable. When I look at this, you might say, let's try to expand it out using the geometric series. 1 over 1 minus x squared, I can multiply by x later, it's 1 minus x plus x squared. And if I try to do this by the geometric series, it's 1 plus x squared plus x squared squared, and so on and so on and so on. If you want to find the x to the 10th term, so many different things contribute an x to the 10th. This is 1 plus x squared. From this one, I'm going to get an x squared plus 2x cubed plus x to the 4th. And so we see, for instance, already for x squared, 2 different terms are contributing. It's going to be worse as we go further and further down. We know the coefficient of x to the n is just the nth Fibonacci. We would love to pull it out, but if I do it like this, it's not going to work. So you say, screw that, goodbye, and you do partial fractions. You write this as 1 minus alpha. Is it this way? So I can factor it, I believe, like this. So alpha times beta would be 1, alpha plus beta would be 1. Wait, is this going to work? No, because I want it to be a minus x squared.
Yeah, you can't do that, right?
Well, I can. I mean, just one of them has to be a positive. I would just say I want alpha times beta to equal negative 1. Right?
Yeah, and alpha plus beta should be.
And alpha plus beta should equal 1. Right? So beta is just negative 1 over alpha, so we get alpha minus 1 over alpha equals 1. Alpha squared minus alpha minus 1 equals 0. So alpha is 1 plus or minus root 5 over 2.
Well, that's a nice number.
It's a nice number. And so when you start expanding these things, we can then write this as a over 1 minus alpha x plus b over 1 minus beta x. And then we expand each one of these. And this one will become a sum of alpha to the n, x to the n, and this one will become beta to the n, x to the n. So it's a sum of alpha to the n plus beta to the n, x to the n, except I dropped the a and the b here. And then we'll shift things because we have an x there. But when you put in all of the little algebra, and again, it's not bad to just go through and do this, you will end up with Benet's formula. That Fn is 1 over root 5, 1 plus root 5 over 2, Vn minus 1 over root 5, 1 minus root 5 over 2 here. One of my favorite formulas in all of mathematics. What does that not look like? It does not look like an integer. You've got divisions by 2, you have square roots, it all cancels out, and at the end of the day, it's an integer. As a nice exercise, what can you replace the 2 and the 5 with and keep it as an integer? But the idea is, we start off by taking the data, the fn's, we combine them into this generating function, and because the generating function has a closed form, we can use that to deduce information about the individual local pieces of data. That's the big picture theme as to why we spend all of our time doing this, is we piece everything together and you get a global object. That global object would be useless if you didn't have techniques that you could use on it. For those of you who know my work in random matrix theory, my favorite result in linear algebra is the eigenvalue trace lemma, that the sum of the eigenvalues is the trace of the matrix. It turns out that that's extremely useful. It allows you to get your hand on the eigenvalues by knowing some information about the matrix. So when we're looking at the Riemann zeta function, the idea is it's connected to the prime, so it might be worth studying, and it has a nice global object that we can deduce information from. So in our next class, we'll talk a little bit about other generalizations of the Riemann zeta function leading up to modular forms. So we've already seen today, and we saw in the previous class, the Dirichlet-Ada function, which is very simple. We replace the ones with an alternating sequence. That's almost the easiest thing you can do. If you've done any group theory or elementary number theory, you've seen Dirichlet characters. That's another thing you can do. And what that will do is that will give you Euler products of degree 1. For the modular forms that we'll need, we will need Euler products of degree 2. They'll be a little bit more involved. All right, this is a good place to stop, and we will see if it recorded at all. I'm very worried.